All right, so let's go ahead and get started. And I see a question about, are the labs that you've done graded? No, I am working hard on getting those exams graded. As soon as I finish the exams, then I'm going to move on to the homework and the labs. I'm sorry, I got a little backed up. I underestimated how much time it takes to actually put all of the homework, or I should say all the exams, onto the internet and then to grade it while it's on the internet. It's just a different experience for me, but once I get it down, then I'm sure it will not take too much longer than usual. All right, so any questions about what we did before break? All right, so here it says calculate the energy of 1 photon of yellow light with a wavelength of 589 nanometers. And here's our equation again, and this one will be given. Here's Planck's constant, which is again going to be given. And then c is our speed of light. Which is also given like so. All right, so what I want you to do is try to plug in and find the energy. Be aware that this is in nanometers, and you need to make a nanometers to meters conversion before you can plug it in. And that is because you have meters right here in the speed of light, so you need to have meters for your wavelength. But any questions on what we're going to do here? All right, go ahead and plug this in and give this a shot. So again, you're calculating your energy, E, and you're using Planck's constant times the speed of light divided by the wavelength given right over here, but you need to convert it into meters. So give this a shot. If you get stuck, feel free to type a message to me, or you can unmute and ask. Okay, so I think I've just put the poll on your screen. So go ahead and click in. Yes, and it sounds like, okay, sounds like several of you would like more time. So let's go ahead and take a couple more minutes. Those of you who are getting values for your energy, feel free to type those into the chat box. All right, I went ahead and put the poll up again, so go ahead and click in if you'd like more time, or if you're ready to go over it. All right, so let's go ahead and take 1 or 2 more minutes because it looks like there's a few people who want some more time. For those of you who are all done, feel free to type your answer into the chat box so you could compare with your classmates. All right, so it looks like Clinton's getting 3.37 times 10 to the negative 33. Anybody get similar or different answers? And it looks like Andrew's getting something similar. All right, so let's go ahead and go over it. So we have Planck's constant and the speed of light up on the top, and then we need our wavelength. So our wavelength was 589 nanometers. So we're going to convert that into meters. And for every 1 meter, there's 10 to the 9th nanometers. So how many meters did you get for your wavelength? Anybody find their wavelength in meters? And they're brave enough to type it in? All right, so I'm seeing 5.89 times 10 to the negative 7. Like so. Any questions on how we find the meters or why we need to go into meters here? All right, so let me move this on down. And this is our wavelength in meters. All right, so let's go ahead and calculate this out. All right, so on the top, 6.626 times 10 to the negative 34. And to that, we're going to multiply. 3 times 10 to the 8th, that's our speed of light. And then we're dividing. 5.89 times 10 to the negative 7. All right, so I am getting 3.37 times 10 to the negative 19, but I saw a lot of 3.37 times 10 to the negative 33. Let me see. I have an idea on how that might have happened. Let me give this a try. So 6.626 times 10 to the negative, negative 34 times 3 times 10, to the 8th. And then when you divide it, let's try 5.89 times 10 to the negative 7. There we go. All right, so the problem here is that in the denominator, and I'm thinking about how I'm going to show it to you. Let me copy this over. All right, so in the denominator, if you don't use the e function, you need parentheses. Get a thicker marker. You need to add parentheses right here. Because if you do not use parentheses, what you're telling the calculator, 6.626 times 10 to the negative 34 times 3 times 10 to the 8th divided by 5.89 times 10 to the negative 7. So if you don't use those parentheses and you don't use the EE function, the calculator thinks the times 10 to the 7th is up on the top in the numerator. So for those of you who are getting the 3.37 times 10 to the negative 33, give it another try and see if you can get this times 10 to the negative 19. So those of you who are getting to the negative 33 before, did you get to the negative 19 now? Yes, okay, excellent. So one of the reasons that I really like using the EE key is that I don't have to worry about those parentheses. But if you did not use the EE key, if you use the times 10, you've got to have these parentheses here. So let me put a little box around this one right here. All right, it's a little sloppy, but this way, if you go back to your notes, or those of you watching the video, these ways right here, those were the wrong ways to do it, and this is the correct method. Okay. Any questions on how we put it into the calculator or anything else here? All right, so here, just to remind you one more time, this is joules per photon. Oh, I'm sorry. Yes, joules per photon. Sorry. There we go. All right, so any questions on anything that we've done with this problem here? All right, so just moving on, this is what we call the emission spectrum. So these are the lights that we see after they pass through the prism, after the prism has split the light. So white light from a light bulb, you can actually see all of the colors. So sometimes we talk about how all of the colors are given off by a light, but say a shirt will absorb some and will reflect others. We talked about that in one of our labs. That is because white light, which is the light coming down from your light bulb, from the sun, it contains everything. But for our elements, each element contains its own spectrum, its own set of colors. And I mentioned earlier, these are a fingerprint. Now, hydrogen has a nice, easy fingerprint, 4 colors, but in experiments, we usually only see 3. Helium's not too much different, but once you get to what we call a many electron atom that has tons of electrons, then you get to see so many of these colors, so many lines. And so neon is one of those. It's got lots of electrons, so we get lots of lines. And neon is a good example of why we really need a computer to identify these elements. So if you're looking at something like neon, you don't want to try to match up each one of those lines. You want a computer to do it for you, and that's why some of our awesome new telescopes have a computer already hooked up to it. So you point it at that star, at that planet, and boom, it can tell you which elements are there, which is super cool. But any questions on these emission spectrums or how we get these? Using that height, using the slit, passing through a prism, and then splitting it into its colors. All right, so we've already had a chance to see the flame test video, but any of you who are like, oh, that was so cool, you might want to, you have lots of time, you might have little kids at home, you want to show them some really cool chemistry. That flame test video is linked here, and it is really, really awesome. All right. So here it says the farther an electron falls, the more energy will be released. So the ladder on the right is showing the approximate energy level diagram for hydrogen. So this is the same ladder we looked at earlier. And one thing I didn't comment on, but I'm going to tell you about now, is that the energy levels are more spaced out closer to the nucleus. So what that means is energy level 1 and 2 have more space between them than 2 and 3. And notice as you go up, they get closer and closer together. So as you get further from the nucleus, the energy levels do get closer and closer. And again, our rule is the farther the electron falls, the more energy that will be released. Just think of it as the further you fall, if you were to fall off that ladder, the more energy that you would absorb and the more pain you would be in. So which of the following transitions does light emitted have the longest wavelength? So I want you to think about this and think about which one of these will have that longest wavelength, and the wavelength is down at the bottom just to remind you. So our low energy has the long wavelength, whereas our short wavelength is associated with high energy. And what I'm going to do is I'm going to put you into breakout rooms just for a moment so you all can talk about this. So I'm hoping when you get into your breakout rooms, you either unmute or you talk on the chat box, and it will just go to your breakout room chat box. So give me just a moment here. I'm going to put you into a breakout room. When you get the option to join a breakout room, please do join it. All right, so go ahead and join those breakout rooms and then chat with your classmates about which one you think it is, A, B, C, D, or E. Sorry. See, about 3 of you haven't joined yet. Go ahead and join that breakout room, and so you can discuss with your classmates which one you think it is, A, B, C, D, or E. Your classmates are very nice. They won't bite. All right, so it looks like we got almost everybody back. All right, so what did y'all think of the breakout room? Did you like it, dislike it? What'd you think? Any thoughts? Went well, okay. So one person liked it, two people like it, okay. Okay, excellent. So Andrew, were you able to actually see my screen still inside of the breakout room? Oh no. Oh, it would be nice to see the problem in there. Oh, I see that. That was the problem, that you couldn't see it anymore. Okay. Oops. Okay, so I could see that that could have caused a problem. I didn't know if you could still see my screen share in there. Yes. So I see a few of you are saying that it was frustrating not having the PowerPoint there. I apologize. I thought you'd be able to see it. All right. At least we know for next time. Okay. So what do you all think? A, B, C, D, or E? Go ahead and type into the chat box. All right. So I'm seeing an E. I'm seeing some A's. A. Some E's. All right, so it looks like A's and E's are our most popular answer. All right, so let's go ahead and take a look. It looks like we're split between the A's and the E's. All right, so here we want to look for the longest wavelength. So for a long wavelength, we're looking for something low energy. So for something low energy, we want to fall only a very short amount. So we want, I'm going to say the smallest fall. We want it to fall the shortest distance. All right, so let's start off with 4 to 3. So 4 to 3 would be right over here. That's A. And then B says 3 to 2. That would be this one right over here. And then C says from 3 all the way down to 1. And then D says from 4 to 2. Let me switch colors here. And then E says from 2 to 1. All right, so we are looking for the shortest distance. So we don't want a really long fall. So this one right here, we don't want. It's a really long fall. It's going down 2 rungs. This one, again, we don't want. It's a long fall going down 2 rungs. So the 3 to 1, I'm going to cross out. And the 4 down to 2, we're going to cross out as well. Now the next question, would it be A, B, or E? So all of those are falling only 1 rung. Let me move this one right here over to the side. Oops. All right, so we are looking at 4 to 3, 3 to 2, or 3 to 1. And I'm sorry, 2 to 1. And we're looking at how far apart those rungs are spaced. So we want it to fall the shortest distance possible. So would the shortest distance be here, the 4 to 3, the 3 down to 2, or the 2 down to 1? What are we thinking? Which one is the shortest fall? All right, so I'm seeing some 4 to 3s. Excellent. Yes, so 4 to 3, because there's not as large of a gap. Here it's between the rungs of the ladder, but in the atom it would be between the energy levels. So we are looking at 4 to 3. All right, so I know there was a lot of you who were thinking about E earlier. What do we think about A? Are we all comfortable with A, or any questions on why it would be A and not E? All right, so the key is that the rungs are closer together near the top. So if this was a regular ladder, those would all be equal in energy. But because this ladder represents the energy levels, it is this one right here, because those rungs or those energy levels are closer together. All right. Other questions on this one right here, or any questions on this one? All right, so we are still talking about quantum mechanics, and here is our next idea, and that is the Heisenberg uncertainty principle. Is 6 the highest energy level from Ali? No, it is not the highest energy level. It's just the highest one in this diagram. But no, we can go up to 7, and in theory, we could go up higher. So if you were doing computational chemistry, where you do it all on the computer rather than in the lab, you would even calculate up higher than that. But on the periodic table, 7 is our highest one. Good question. All right, so here again, quantum mechanics, and now we're talking about the Heisenberg uncertainty principle. And the principle essentially tells us that we can't know the speed of an electron and its location at the same time. Everything's based on probability. We know approximately how fast it's going, and we know approximately where it is, but this principle tells us the better you know the location, the worse you know the speed. And the better you know the speed, the worse you know the location. So I'm going to jump over this for just a minute to show you the cartoon, because I think the cartoon helps to understand it a little bit. So it says Heisenberg was caught speeding, and the police officer said, "Do you know how fast you were going?" And he said, "No, because I know exactly where I am." So the better you know your location, the less you know about that speed. But if you know your speed really well, then you know nothing about your location. So here that is in words, that it's impossible to be certain about the location and the momentum of an electron at the same time. And momentum is similar to our speed. Those of you in physics know all the details about the differences. For us, we're going to call it similar to speed. The more certain we are of the location, the less certain we are about its momentum or speed. And the more certain we are about the speed, the less we know about its location. So here it is out in writing. Delta X tells us about the position. So where exactly is that electron? And here is our momentum or speed. How fast is it going? And so what we see is the narrower one of these is, the wider the other one is. So if I can say, hey, it's moving between, and I'm just going to make up some numbers here. Let's say it's moving between 25 and 30 miles per hour. That's a pretty narrow range. I don't know much at all about where it is, but if I could say, hey, I know it's probably in building D of the building D at the LAC campus, probably don't know too much about how fast it's moving. So the more you can narrow down one of those terms, the harder it is to narrow down the other one. So the way this equation works is the product of the change in location and the change in momentum are a constant. So the more precisely you know one, the less precisely you know the other. All right. So what I'm going to tell you, this right here is background, as is this. So remember, I hate to tell you, hey, you don't need this, it's not on the test. So instead I say it's background. It is to help you understand the things that we're doing, but no, it will not be on the test. I will not test you on these. What I do want you to know, and what I could test you on, is this right down here. So I want you to understand this. But what's up at the top here? The equation and those variables, that I don't need you to memorize it. It is good to have it in the back of your memory to understand everything else, but I'm not going to test you on it. You don't need to memorize that equation or use that equation. All right, but questions about that Heisenberg uncertainty principle? I know it's kind of a weird thing. Okay. All right, so the Heisenberg uncertainty principle allows us to talk about electron orbitals. So last semester you probably talked about the S, the P, the D, and the F, and we're going to talk about those again. But the idea of the uncertainty principle is we don't really know where our electrons are. So if you just look at this right here, it looks like, wow, that atom has millions of electrons. That's not the case. So what this is a probability drawing. So if you've taken statistics, you may have seen probability maps. And so what we're saying is these dots represent where it is likely that we're going to find an electron. So where it's very dense, where you're seeing lots and lots of dots, there's a pretty good chance of finding the electron there. Where you're seeing only a few dots, like we do here on the outside, it might be there once in a while, but not very often. So what we see here is that our electrons are clustering near the middle. This is where they're going to be most of the time, but they might occasionally go out to the outer parts of the orbital here. So here we say there's a 90 to 95% chance of finding the electron in its orbital. This is its ground state, and what we just learned is that it can jump to another energy level. It can get excited. So 5 to 10% of the time, it's going to be excited. It's going to be somewhere else. But most of the time, 90 to 95% of the time, it's going to be right where we expect it to be, in these orbitals. And here we call these a sphere of probability, and we refer to this one as the S subshell. But any questions on anything here? All right, so it does look like a circle here, but I want to emphasize it's not a circle. I'm a very poor 3D drawer, but I'm going to give it an attempt. I don't know, that probably does not look anything like 3 dimensions, but I want you to imagine a round ball. So this is a full sphere in 3 dimensions. It's not just a circle. And I know my highlighted drawing does not look anything like a sphere, so I'll get rid of that. All right. So again, our orbitals are based on the probability because we cannot know exactly where the electrons are. So electrons can be found in the orbitals, again, 90 to 95% of the time. And again, this is the sphere of probability, and the one you're looking at right now is called the S subshell, or we often refer to it as the S orbital. So any questions on anything here? All right, so you might be wondering, hey, that's a really cool probability map. What was the equation, the mathematical function that helped us to create this? Or you might not have been thinking that at all, but it comes from something we call the wave function. So the wave function gives us that probability, and here we represent it by psi squared. And I know psychology uses that psi as well. I've always wondered why they use it, but we use it to represent probability. So psi is the wave function, while psi squared becomes our probability of finding an electron in a certain area. And it is a mathematical function similar to f of x. And that function has several solutions. So just like if you were to solve a quadratic equation in algebra class, you could get 2 solutions. Here we get 4 solutions. And those solutions we've labeled S, P, D, and F. So the orbitals that you know of, the S, P, D, and F, they are individual solutions to the wave equation, which we also call Schrodinger's equation. So it gives us a whole set of functions that are solutions to that equation. All right, so here are just a few things to remember. Orbitals are areas of electron density or probability density. So in other words, it's likely we find the electrons there, but on a given moment, we can't be sure they will be there. They may have become excited and traveled somewhere else. Every orbital has a specific shape, and we'll talk about the shapes for each one of these. And I mentioned quantum numbers before. We are going to use quantum numbers to describe the electron in the orbital. So again, think of those quantum numbers as coordinates on a grid. That will help us identify exactly where the electron, I shouldn't say exactly, it helps us to identify the range of an area where that electron will be found. All right, sorry, that wasn't a great explanation. So it will help us to find where that electron will be found through those coordinates, but it's not an exact location. It is telling us which orbital it's in. All right, so questions on anything here? All right, the first thing that I really need you to know is your blocks. So if you have a periodic table handy, I would get that out and go ahead and mark your blocks. And these are the same blocks that you learned last semester. So we have our S block here on the left, our P block on the right, the D block is right in the middle, and way at the bottom is the F block. Now helium is tricky. Helium does not belong to the P block. It actually belongs way over here. And I put this note here, helium is actually an S block element. So helium does belong to the S block, but it sits on top of the P block. Way back when, in the older periodic tables, helium had two locations. It would sit on the top of the noble gases because it's a noble gas, but it would also sit right over here because it is truly an S block element. So you got to remember helium belongs to the S block. But any questions on our blocks are S, P, D, or F blocks? And anybody want a little more time on this to mark the blocks on their periodic table? Yes, okay. So go ahead and take a minute, take out those periodic tables and mark those blocks, S, P, D, and F. All right, how are we doing? Anybody want this slide for a little longer? Yeah. Okay, so I see a yes. Okay. Any questions about anything that we've done so far? All right, so let's go ahead and keep going. And here I've got another cartoon. So at the bottom it says, unwittingly and against his mother's advice, Vince, the first row transition metal, has been lured far from home and now found himself surrounded by the heavier elements of the P block. So just a little chemistry humor. So chemists do love their blocks. So when you go to graduate school, if you go to graduate school in chemistry, you tend to have a specific block that you specialize in. So especially our inorganic chemists, which are chemists that deal with metals, they will be S block or P block chemists, and sometimes you're an S and P block chemist, which is super cool. And then there's the D block chemists, and then there's the F block chemists. So my advisor was an F block chemist, so that's why we focused on F elements. So we looked at uranium, neptunium, plutonium, and all of those, but everybody thinks their block is the best. All right, so questions on anything that we talked about so far? All right, so now each of our blocks also has an energy level associated with it. And before we do this, let's go ahead and jump to our periodic table. We have one. All right, so earlier we were talking about those rungs on the ladder, and we were saying n equals 1, n equals 2, and so on for the rungs on the ladder. And you might be wondering, well, how does that relate to the periodic table? And those are going to be our period numbers right over here. So we see period 1 goes right across here, hydrogen and helium. Period 2 is going to go straight across here. Period 3 comes right across here. And now something strange happens when we get into the D block. So 4 is here for the S's, and it's right here for the P's. But when we get to the D block, what we're going to find is we drop in number. So this is actually the 3 D's, because in D, let me get a darker marker here. So these are the 3 D's. And so whenever you're in the D's, it is always what we call the row minus 1. That is always for your D block, and we'll be talking more about that. So same thing happens for the 5th row. So it is the 5th energy level here for the S's and the P's. But when you're in the D's, it drops 1, and it becomes the 4 D's. Same thing for the 6's, so 6S. There is our 6P. And right in the middle here, we have 5D. Because again, in the D block, it's always the row minus 1. Here are the 7, so there's 7S, 7P, and then, I'm recording. Let me double check and make sure the recording's going. It should be. Yes, the recording is going. Is the sound coming in and out? No, okay, good. But yes, I am recording. I always record. So we have some people who are whose work schedule changed, so they can't make it. All right, so going across that 7th row, we have 7S, 7P, but in the D's, it's going to be a 6D like so. And we're going to talk a lot more about this when we do our electron configuration. But I just wanted to show you why in this slide right here, you see the 1S going across. Oops, let me stay with my colors. 1S. Here's 2S and 2P, 3S and 3P, and then once the D's get involved, the 4s are only for the S and P, and the D's always drop down 1. Now, one thing that I'm going to recommend to you for the F's is not to worry about the rule. Oh, and I see, are they all row minus 1? And for the D's, they will be, yes. So the D's right in here will always be row minus 1, yes. And there is a similar rule for the F's, and the F's will be row minus 2, but because there's only 2 of them, my recommendation is that you just remember these as 4F and 5F. It's easier to just remember those 2. All right, again, we're going to see a lot more of this when we get into our electron configuration. I just wanted to show you right now how these and the energy levels that we looked at earlier, n equals 1, n equals 2, and so on, how those relate to what we're doing on the periodic table. And we have a great question from Jervin. Are the F's the last to be filled? And no, everything's actually going to get filled in order. And way back when, we talked about where those F's actually come from. And this dark line actually represents the F's. So these right here, oops, sorry about that. All right, these right here actually belong right here. So where the F's get filled is as soon as you cross over the line. And again, we're going to talk about all of this when we do our electron configuration. But they're not the last to be filled. They get filled in order. So if you notice, 57 is lanthanum, and 72 is hafnium. When you cross that line, you've just filled all of the Fs. But again, don't worry, we're going to get through all of this in electron configuration. All right, but any other questions so far? All right, so next up, I want to talk about the S's. So here we're going to look at the 1s, the 2s, and the 3s. So we're looking at these right here. And the energy levels don't actually sit the way we thought they did or we imagined them to be on a ladder. So on the ladder, it looked like this is 1, 2, and 3, and they're just vertical, but they're not actually vertical. What happens is these spheres fit one inside of the other. So to me, they remind me of Russian dolls. I don't know if you ever got a chance to play with these when you were a little kid, but the smallest one fits inside, and so it's like 1s, 2s, 3s, 4s, and 5s. They all have identical shape, and they do all fit one inside of the other. So if they were sitting together and you were to cut them open, this would be your 1s. Here is your 2s, your 3s, and so on. So the 1s is the core, the 2s just fits around it, the 3s around that one, and so on. So here when we're looking at these images, when you see the 1s, it is the tiniest one, but what happens with the 1s, very similar to those dolls, is that it is solid. So if you were an electron in the 1s, you get to travel anywhere within here. However, if you were an electron in the 2s, you can only travel in your sphere that is outside of the 1s. So the center is the 1s, and then we have something that we call a node, and the node is that space in between the orbitals. It is like the space in between the rungs of the ladder where we said that we cannot be and that the electrons cannot be. So an electron So the electron, if it's a 1s electron, it can travel around inside of here. Let me grab a better pen. It can travel around inside of here if it's a 1s electron. And if it is a 2s electron, it travels outside of here. But nobody should be in that white area. That white area is just for transition. It is you got excited and you jumped from the 1 to the 2, but you cannot hang out in that white area. And that white area is what we call a node. So the node is the white area where nobody is allowed to hang out. It is, again, just like this area between the rungs. So between the rungs of the ladder, you can pass through, but you cannot stay there. That's what our node is. So just to take a look at the 3s, I'm going to look at this picture right over here. And if I was a 1s electron, I would live right in this area. If I was a 2s electron, I would be living in this outer area. But between those two, there is an area that we can pass through briefly, but we can never hang out in. And that is the node that I just colored in white. All right, now we have our 3s. So if you were a 3s electron, I'll do this in brown, you would get to be out here in the third shell. But again, there's a node between any two orbitals. So here is our node. And the node is the area where electrons cannot hang out, they can only pass through. All right, so let's take a look at how this would, what this would look like if we were talking about those Russian dolls. Oops. All right, so first off, I'm going to think of the 1s electron. So if you are a 1s electron, you get to travel, oops, let me do it in this one. You get to travel anywhere within this doll right here, because it is a nice solid doll, so you get to travel anywhere around here. So you got lots of space to crisscross back and forth. But if you are a 2s electron, you can only travel around in this shell right here. So let's see. You are bound to that shell. And again, in between, you have a node. And so that node goes right in between the 1s and the 2s. Now, if you're a 3s electron, you get to be in another shell further out from the nucleus. But again, there's a node between you and your neighboring shell. So the only orbital that is solid, where the electrons get to go anywhere they want, is going to be the 1s. It's going to be the first energy level, and that's the one I have colored in green here. So if you are in this center doll, if you are in the 1s, you get to crisscross anywhere, but the 2s, the 3s, and so on, all you can do is travel around in that shell that's outside. And in between any two orbitals, there's always a node that you can briefly pass through, but you can never stay in. So I know that's kind of weird and tough to grasp, but any questions about this idea that one sits inside of the other, which sits inside of the next one, just like the Russian dolls, that only the 1s, only the center is solid where the electrons get to go everywhere. Any other ones can only roam around in their shell. Yeah, yes, they can travel between shells, so long as they get enough energy to get excited, then yes. And assuming that the other shell is not full. So for example, if the 3s got excited and jumped to the 4s, then there'd be room in the 3s for the 2s to move in. So yes, they can definitely travel between shells if energy is added and if there's room available. All right, so any other questions? I know this is kind of a weird thing to wrap your head around. Okay. All right, so next up, electron probability and the p orbital. So the p orbital works in a very similar manner. And here we have kind of these fuzzy orbitals. They're again showing the electron density. So if you took your intro to chem class last semester, you probably learned an orbital that looked like this, and you call this the p orbital. And this is often how we draw it. It's officially called a dumbbell shape, not because we're trying to be mean and insult it, but because once upon a time somebody thought it looked like the kind of weights that you'd see in a gym, the free weights that are called dumbbells, but it does not look like a free weight to me at all. But this works in a similar manner, and the node happens to be right in the center here. So the node, as it says above, is an area of zero electron probability. What that means is probability-wise, there's zero likelihood that we'll actually find the electron there. That is because it jumps from one lobe to the next. Jumps very, very quickly. It passes through that node so quickly we cannot find it there. It does go through, but very, very quickly. And by the way, these are two lobes of the same p orbital. And it works the same way. So again, my artwork is not fabulous, but let me give it a shot just to show you how these work. So if this is the smallest p that we have, and we do not have any 1p's, so the 2p is the smallest we have, then it would be solid. So if you were a 2p electron, you get to travel anywhere around there that you want. But now in the 3p's, it becomes a shell like that Russian doll that's just a shell. This is now the 3p. And notice I've left some white space between them. That white space is the node. And now this right here is going to be our 4p. And 4p is another shell. So if you happen to be a 4p electron, you could only travel around in that 4p shell. So here we have nodes first right over here in the center. But we also have a node in between each shell, just like we did for the S. So right here, that's another node. Right over here, it's another node. So the nodes are essentially spaces in between the different energy levels of these orbitals. So between the 2p, the 3p, the 4p, and so on. But the p has an additional node right in the center, because electrons are not supposed to hang out in the center. They can either be in the top half or the bottom, but they should not hang out in that center area. Okay, so questions about the p at all?
Electrons in the 2p are stuck and they can't move at all, but electrons in the 3p and 4p can move.
Any electron can jump up if it is excited and there's room in the next orbital. So it's always possible for it to travel. It just has to pass through that node quickly and move on. It can't stay there.
Okay. Thank you.
Mm-hmm. Other questions so far? All right, so sometimes students say, well, what exactly do you want me to know from these in addition to the idea of the nodes and how the orbitals sit one inside of the other? I do want you to know that our s orbital is spherical. I'm going to draw it as a circle. Some of you are much better at drawing 3 dimensions. And feel free to do 3 dimensions. Normally, I would say on a test or quiz, I could ask you to draw it, but since we're doing online, if I were to give you several shapes, you should be able to identify the s orbital. And I want you to know that there's only one type of s orbital. There's only one type of sphere. It is round. However, when we move on to the p orbital, we're going to see there are 3 types. But first off, for the p orbital, I would want you to be able to, well, normally I would say to draw one. Now I'm going to say to recognize one. And it's going to look something like that, something like a figure 8 or an infinity sign. And there are 3 different types. And by 3 types, what I mean is really the same shape, but in 3 different locations. So here we have what we call a px, a py, and a pz. So one is going to sit on the x-axis, one on the y-axis, and one on the z-axis. And I'm going to show you images of those in just a moment. Let me make sure this is obvious that these are all for the p orbitals. Okay, but any questions on anything so far? All right. So here are those p orbitals, and let me zoom in here. Here's the px, the px, the py, and the pz. So in your math class, you might have seen a 3-dimensional coordinate system, x, y, and z. So here's just saying that we have one p that lives on the x-axis, one that lives on the y-axis, and another one that lives on the z-axis. And when they all sit together, they look like this. So that one's a little hard to imagine, so we tend to think of our p orbitals as 3 separate ones, but these are all for the same energy level. So these could all be 2p's, and then you will have a set of 3p's that go around every single one of these. and so on. So it gets very complicated looking, and that's why we like to break it down into these, what they call dumbbell shapes, but they, I don't know, look like two balloons tied together to me. All right, but any questions here? All right, so next up are the d orbitals, and there's a total of 5 d orbitals. So the d orbitals have what we like to think of, or at least we call, a 4-leaf clover shape. So they actually look like 2 p orbitals put together, except for this one right here. And this one looks like a p orbital, but it has a ring of electron density around the center. So normally I would tell you that you're responsible for being able to do a simple drawing of them, and as you can see, my drawings are quite simple. But now what I'm going to tell you is you are responsible for recognizing that any of these are d orbitals. I would not give you the overall diagram because this one right here is crazy looking, but that's what they do look like when they're all put together. But you are responsible for recognizing the individual d orbitals. So if I give you something that looks like, that looks like this, or that looks like this, I would give you the actual diagram. So it would look like this. So those ones I want you to be able to recognize as d orbitals. Next up, we're going back here. So I want you to know about the d orbitals. There are a total of 5 types of the d orbitals. I'm not going to make you memorize all of the prefixes for them. There's the dxy, dyz, and so on. I'm not going to make you learn all of those, but I do want you to know that there's 4 that look something like so, plus 1 that looks like so. So I want you to have that idea of what they look like and how many there are total. So any questions so far about the d orbitals? All right, so next up are going to be the f orbitals. And what I want you to know about the f orbitals is that there's 7 types. Oops. So 7 types. I'm not going to make you memorize what they look like because they get kind of crazy in the f's. So here are the f's. They are a little odd looking. So this one right here sort of looks like the d orbital, except that it has 2 rings of electron density and it's actually separated. And you see that same one in 3 different planes. And then over here, sort of looks like the d orbital, except you've got 2 of them, 4 lobes going up, 4 lobes going down. And you see it here in 4 different areas. So those are your f orbitals. But again, I'm not going to make you memorize all the f orbitals. I just want you to know that there are 7 of those, and that'll become handy when we do our electron configuration and orbital diagrams. So any questions about the orbitals or what I want you to know from them? All right, so what I'm going to ask you to do between now and the next time I see you is refresh your memory on electron configuration and orbital diagrams. So we have the 2 videos that I posted up there. So those are videos just like for those of you who are actually watching this on video, it's very much like the video that you're watching. It's just me talking and writing on the iPad, and it's a lecture that I did for the introductory class. So 2 videos, they're both about 30 to 45 minutes, and it's a great refresher on what electron configuration orbital diagrams are. For those of you who haven't had this for a while, it is a great introduction to them. So it's going to go through these first few slides. And then where we will pick up is right here. Next class, we're going to pick up with the irregular configurations. So what we're going to do together is the new stuff. So irregular configurations, ions. But this other material, it is review material, so I'm going to ask you between now and next class, please watch the videos. Again, 2 videos. They're linked in the videos section on Canvas. So they're not too long, so please do watch those before I see you next time. But any questions about what we talked about today? All right, so let's go ahead and take a 10-minute break. When we come back, we're going to talk about the lab. So it looks like it's almost 7:10, so let's come back at 7:20.